3, 2, 1. Let's go! I'm the host of the PVE podcast, sitting down with Geary Schindel, and I'll pass the mic to him in a minute. But what needs to happen is a thank you to Trunkline.com, a revolutionary marketing tool. And what they're doing is allowing you as a provider, as a service provider, and even a consultant. You put your projects up online, the before, the after, what you learned, what your major takeaways were, where you save time, where you save money. And as a company, you can build this project portfolio through their website. And then once you do that, you upload your projects, it goes to work on the marketing. It gets it out there through all the social media channels for you, help you on the SEO and all those things that happen with Google. It's a really cool website and something that I totally believe will help many service providers continue through these times, no matter if it's a global recession or not. Services to keep our energy demand under control, services for fresh water, aquifers, and developing all those things. Who's drilling the best wells? Who's doing it with the best practices? Trunkline's capturing that. It's kind of an Angie's List, if you will, for the services that are being provided for the natural resource industry. So that's really exciting. The other thing I want to mention real quick is the South Texas Geologic Society Christmas party. I assume you're going to be there.
Yes.
All right. It's December 15th. We're still looking for sponsors. We're always looking for help on those events. And so on behalf of the South Texas Geologic Society, everyone has an open invite to come and hang out with the geologists of South Texas, the engineers, the people that are in these natural resource industries, and just a great night for networking and to just say thanks for all the hard work for the year and to celebrate the end of another amazing year and get ready for the next one. So December 15th, reach out to Justin Sharp, justinwsharp@gmail.com with the STGS for more information there. And now, Gary, please make a quick introduction. Who you are.
Well, first off, the Christmas parties with the STGS are always a lot of fun, so I encourage you to go. My name's Geary Schindel. I am a professional geologist and karst hydrogeologist living in San Antonio, Texas.
Right on. Okay. You've recently retired.
Recently retired. Also past president of the National Speleological Society. And I've been a caver and geologist for about 40 years.
Man, your cave stories got me going, got my juices going. One, because I just kind of have this claustrophobia-ish feeling when I'm in there. So I'm always kind of get the chills when I think about people in caves, and then you telling me that you got a 4-inch space of oxygen, and you're crawling through cracks, and man, your story was fascinating. And
back when I was younger and dumber, it's amazing what you'll do for $4.25 an hour.
Well, you were having fun doing it.
We were.
And, man, you're still here today to share that knowledge and wisdom and what you learned, what worked, what didn't. That's incredibly valuable. And so I really appreciate you taking the time to walk us through that. And, one of the things that always crosses my mind, or certainly has been on my mind ever since my undergrad, was this water problem, this fresh water problem and water wars, and the idea that, that's going to be the next biggest thing in natural resources is the fresh water scarcity problems, and how are we handling this situation? What's your outlook for the next 5-10 years, or maybe even call it 50? What's fresh water? Where's it going?
Well, population increases demand. So to meet that demand, there's a couple different ways to do it. One is to try and develop more resources. The other method is through conservation. And I think it's important that you have an active program in both, and that you manage the resource so that's sustainable. Okay. Otherwise, you're going to be mining groundwater and creating other problems.
Wow. Yeah, if we can get a notice to my neighbor who waters his lawn 17 hours a day and it floods my yard, he's watering it so bad, and I got a dog that's back there. It's an in-house dog, so it gets all muddy, and now we got to deal with that problem because this guy's watering his lawn too much. It's like, hey, man, conserve a little bit here. There's some rules.
Yeah, there is. That's a difficult issue. How do you convince or coerce people into using less water and being more conservation-minded in their water use? And it runs from everything from watering their grass to what kind of food you take in, because the amount of water being used for things like growing beef versus growing corn or growing other crops in that is immense. Wow. I mean, I think I read over 1,000 gallons required for 1 pound of beef.
1,000 gallons of water for 1 pound of beef?
I believe that's the case. I'll have to look up the number, but it may be even greater than that.
Wow. Yeah, I never even thought of mass balancing, what that is. Yeah. As far as the watering and stuff, I'm super interested in technologies that can just use less water and be more efficient with the elemental exchange and the gas exchange between the soil and the grass. You know, what's actually making it grow. If you just hit it with dead water that's not very active and doesn't have much way to interact with those soils elementally and chemically, you're wasting a bunch of water just trying to, you think more water is going to help me grow my grass. No, it's this distribution of those elements that break down the soils that's releasing gases and feeds the plant. Yep. There's got to be some modern technology too that needs to be developed in these areas where I love flourishing grass. I love good grass, but if it's not naturally doing it from the rainwater and stuff, I kind of sit back and think, well, why do I have to water it more? There's something else going on there. Yeah.
Well, or whether you should have grass. I mean, part of our issue is we live on the edge of the Chihuahuan Desert, but some people want to have a yard like they live in northern New Jersey. So I'm not sure that those are compatible. But I think the number I've read is about 70% of all water being used in the summer months are for irrigating grass.
Oh,
and as some people say, you water the grass so you can mow it, and you don't even eat the grass clippings, so or feed them to anybody. So anyway, why are we growing this giant monoculture of grass? Maybe xeriscaping and some other techniques may be more efficient in saving water.
Yeah, I just moved from Arizona. We had that landscape of our whole yard. It was like a house on an acre, and it was all just desert and rock and cactus and stuff. Like we had turf in the backyard. I don't know about that recycled plastic turf stuff so much, but still, I mean, it was, it's very beautiful landscape without the need of watering and cutting your grass. Also.
Yeah, but you see, Arizona is probably one of the prime areas that's going to have to wrestle with the incredible growth that's occurring in the Phoenix area. You see ground subsidence issues from overpumping. There's massive amounts of irrigation that are being done, and much of that is inefficient flood irrigation. Whereas in Texas, we've incentivized farmers to basically put in center pivot systems that are much more efficient. And so Arizona's going to have to make some choices, about whether they're going to how they're going to conserve water and utilize what little they have. And you're seeing that now with the fact that Lake Mead is about as low as it's ever been since it was filled. There are issues that they're looking at cutting off the amount of water next year if we don't have a decent snowpack.
Las Vegas citizens and stuff.
Well, to the whole Colorado water compact area.
Wow.
So so they're in a very prolonged and very deep drought out there, and they're going to have to address some of these issues very seriously. The Edwards Aquifer Authority implemented a program where they helped farmers take loans out to put in center pivot systems, so they use about half of the water that a flood irrigation system used, and then they were able to actually sell that water they saved over to some of the cities, which paid them, basically for that water right.
Fantastic.
So the water market seems to have really helped with conservation issues.
Wow.
And then, of course, the city of San Antonio and some of the other cities have also implemented some really great conservation programs with low flush toilets, restrictions on water, water use for irrigating lawns and that, and restricting the amount of water that can be, or the times of day that water can be applied. They have a number of other, conservation programs in effect too.
Interesting.
So you got to work on both ends. Looking at supply and making sure it's managed so it's sustainable.
Yeah.
And also to conserve, water so that you're using it wisely.
Yeah. Yeah. So much dropped out of the show in all kinds of little ways, little epiphanies as you were talking about things. And one of them was this idea, this bad water line, and how through geologic time in the Edwards, it seems to be migrating deeper in the aquifer, increasing permeability as it does that through this positive loop that you talked about.
Positive feedback loop, right.
With the sulfur and how it's creating this sulfuric acid, and that's creating porosity and permeability as it's moving through geologic time. Such an interesting concept, and one that gives me confidence and some security, and maybe I sleep a little bit better knowing that, as our aquifer, the freshwater side of it, it's getting bigger, and we're getting more fresh water and easier ways to flow that fresh water to these wells that we already have. So we need maybe less drilling in the future. You can start arguing that, nature is giving us a more reliable natural resource. That was pretty cool to kind of put that together.
Yeah, the aquifer is enlarging. I mean, you can just look at the concentration of calcium and bicarbonate in the water discharging out of Comel Springs. You can calculate, roughly how much increase in porosity through the removal of the limestone is occurring across the water, across the artesian portion of the aquifer.
Wow.
So if you think about it, the problem is it's micron by micron along the walls of a conduit over time. So you and I probably won't in our lifetime see a significant increase, and it would be extremely hard to measure other than to approximate it looking at, this mass transfer removal of calcium carbonate out of the springs.
Yeah.
It's coming from the walls of the conduits in the aquifer.
Wow. And parts of the aquifer are going to have higher bicarbonate because it's doing it more efficiently? Is that what?
Well, it's just the dissolution process is occurring.
Right.
That's still occurring, and that byproduct of that dissolution is the calcium and bicarbonate that's discharging out of the springs.
Yeah.
So you can say yes, the dissolution process is still occurring.
Yeah.
From the contributing zone, the recharge zone, as well as the deep artesian portion of the aquifer.
Man, that was one thing I wanted to bring up in the show, and just maybe a quick comment about carbon and CO2 sequestering into the rock, and also being put in the solution. It's in the water, CO2, and it's super important.
Small amounts, yeah.
Small amounts, but it seems to be very important to these aquifers.
Right. I mean, in theory, increases in CO2 should make more, in the atmosphere, should make more carbon available to, in the water, which, in theory would, cause an increase in dissolution rates. But again, probably not a lot, that you could measure. And that, as far as sequestering carbon, limestone's a good place to do that.
Mm-hmm.
The question is are we making more limestone, or are we affecting because there's more CO2 being dissolved in the oceans also, are we affecting the pH of the ocean, which causes less material to precipitate out? So if you think about it, one of the concerns with increasing CO2 levels is whether some of the biologic communities that rely on calcium carbonate, basically, can they precipitate it out if the pHs continue to decrease? Yeah.
Interesting. So the carbonate factories, like the shorelines and whatnot, with pH decreasing.
Right. Becoming more acidic.
More acidic.
Right.
The pH is decreasing in the oceans. Is that a fact?
Yes. Oh, absolutely.
The pH is decreasing in the oceans. The oceans are becoming more acidic.
Right. That's the major area where most of the CO2 that's in the atmosphere is being absorbed now, is in the oceans. And so one of the questions would be, is how much more can it absorb, and what kind of impact does that pH have? That acidification of the oceans has on precipitating out calcium carbonate.
Wow, isn't that interesting?
Yeah.
And the idea of anthropogenic carbon creation going into the atmosphere it's getting sequestered into the ocean?
Not all of it, no. That's why you've seen an increase in CO2 levels. They're over 400 parts per million right now.
Right.
And up from about, 250, I think it was, 270.
Definitely dangerously low levels for sure.
Yeah, industrial, pre-industrial revolution, I think the CO2 was around 250, I think. But again, this is not my area of expertise. But we've got an increase in CO2 in the atmosphere. It's from basically burning hydrocarbons, and it's having impacts on climate on a global basis.
Yeah, that's definitely a rabbit hole we'd have to go down in like episode 2 on exactly what's going on there. Because the process of serpentinization, which is making the ocean basins and the ocean floors, that process that makes serpentinite in the ocean floors, is a massive CO2 release.
Right.
It's a massive methane and CO2 and just a crazy, huge process that's going on, and it's going on across all the oceans. So the scale of it and its contribution, which you can see in geologic rock record, we might be ramping up in a time of serpentinization, which has happened several times in the past. That could be contributing a lot to this increase as well.
I'm concerned that we maybe don't understand that process as well as we could or should, and it could be having kind of a dire impact.
Yeah. The oceans are heating up. It appears it's very, very interesting what's really going on there, and there's definitely good research, going in that direction, but. It's kind of late, that seems like we could have been, really studying this.
In warmer oceans, calcium carbonate, if I remember correctly, is more soluble in colder water than warm water too. It's not intuitive. You would normally think that, you can dissolve more materials in warmer water than you can colder water, but my understanding is that the carbonates are fairly more soluble in colder water.
In colder water.
Yeah.
Oh, so that's not good. So if it's heating up, that's another slowing down the absorption rate.
Right.
Interesting. I wonder if there's a correlation there with what's going on in the atmosphere too.
There are certainly people who are more knowledgeable than me that would be people that you would want to ask about that. But
it's interesting.
That's my understanding.
Yeah. No, interesting. As was this entire show. This episode is brought to you by Trunkline. You probably know Trunkline as the company that makes the legendary oilfield horizontal drilling socks. And it's true. Our Drill Baby Drill socks featuring a heel-to-toe wellbore are 100% American-made and are designed right in the heart of the oil and gas industry. But did you know that Trunkline is also a revolutionary digital marketing tool that can transform the way you advertise your oilfield services? For only $800 a month, you can showcase your company's project track record on Trunkline, and our automated platform will boost your exposure through social media, email marketing, SEO, and more. Now, whenever one of your new customers asks you, "Can you show me an example of your work?" you can simply turn them to your Trunkline portfolio. It's more effective than a brochure, it's less expensive than sponsoring a hole at a golf course, and easier than maintaining your website. Join more than 200 service companies on Trunkline by signing up at register.trunkline.com today. Let's go. Well, let's start the conception part of the PBE podcast, and it's Geary Schindel, right?
Right.
Geary Schindel.
Yeah, Geary.
Yeah.
It's not my fault, and I have no explanation why. Why it's spelled that way.
I was thinking maybe you're Canadian or something.
No, it's unique.
Yeah, it is.
The family legend has it that my parents decided on the name. My cousin, I guess, wanted to spell it, and she named me after some B-grade movie star in the 50s who I've never found. So my parents laugh, and I don't know if that's true or not.
So, it sounds like a good story.
Yeah, as good as any, I guess.
Well, where are you from? What?
Well, I grew up in Montgomery County, Maryland, right outside of Washington, D.C.
Yeah. Wow. Okay. Cool. Geology is really cool out there. Fascinating.
Well, the Piedmont, yeah, and we live very close to Great Falls, Maryland, which is where the Potomac River cuts a gorge, as it comes off the Piedmont into the coastal plain and the fall line. And so there's some wonderful and very bizarre rock outcrops there along the Potomac River and along the cliffs there.
Right on.
Yeah.
So when you were a kid, you got to walk up and down all that stuff?
Well, on occasion. My parents didn't like, because it's also a Class 6, whitewater, and it's one of the more dangerous national parks because it's so close to a large population center. And, there's serious water, and of course people go there and enjoy, their time along the rocks, and sometimes they fall in. So it's, I think only the very best boaters have actually been able to kayak the most of the rapids there.
Wow.
It's very impressive.
Wow. Yeah. My experience of understanding the physics of water, because you really don't get it unless you feel that power. Certainly the ocean, undertows and the waves. Growing up in California, I was able to understand how powerful water, it really is. And that goes to the podcast that we're talking about. Like it's amazing what even calm water, what appears to be calm water, like 10, 15 feet deeper, if you jump into it off a cliff or anything like that, there could be roaring, underneath. It's very, very fascinating. Water is so fascinating. The structure of it, how it interacts with the real world, how it interacts with nature, how important it is that we live on this water planet, how we understand, water. So tell me how this goes. How does the story of Geary becoming a hydrologist, right? How does that go?
Well, I've been interested in geology since I was a young kid, which is, I understand, fairly unusual. Most people, get into it by taking a survey course in college and that. But I knew I wanted to be a geologist from about the age of 12.
Wow.
And then at the age of 14, I was old enough to join the venture, or actually it was called Explorer Scouts at the time.
Nice.
I was a Boy Scout, and it was older kids, 14 to 21, and it's co-ed. And that group specialized in caving and canoeing. Exactly. And so at the age of 14, I went into my first cave and then decided I wanted to study caves, which is a pretty unusual niche. I spent 2 years at the local community college, Montgomery College in Maryland, and excellent education. And then went off took a year off and worked to save money to go to West Virginia University, which had a good program on groundwater and in particular caves and karst. So went there, spent 2.5, I think, more years going to school, and then went to graduate school at Western Kentucky University in Bowling Green, Kentucky, where they had a program that specialized in karst hydrogeology.
Wow. So how did the connection between West Virginia and then Western Kentucky, how did you, of all opportunities, of all schools, how did that connection happen?
Well, they had a researcher there, Dr. Nick Crawford, who had developed a program specifically on caves and karst, and Bowling Green is situated on the Mammoth Cave Plateau, the Pennyroyal Plain, basically. So there were caves basically on campus and some large groundwater basins. He'd done a lot of research, and they also offered money. So graduate assistantship, right?
Things are lining up here.
Right. So I worked there and graduated in 1984, at the end of 84, and at the same time was working as a Park Service physical science technician at Mammoth Cave National Park under Dr. Jim Quinlan and that. And then before between West Virginia University and Montgomery College, I worked on a tunnel boring machine.
On a what?
So we were drilling tunnels under.
A tunnel boring machine.
Yeah, TBM. Yeah, so.
Tunnel boring machine. Yeah. How big of a hole can that thing make?
That one was only about 6.5 feet, so it was actually a small machine. Yeah.
6.5 foot diameter hole.
Right. Yeah. So.
And how long could it drill?
As long as you can feed it, rail and pipe and power.
Oh my!
And don't wear out the bits. And that. So it was an interesting job. It also motivated me to get back to college. We were making. I was making $400 a week at 60 hours, so it came out to about $6.60 an hour. Yeah. My first job was basically holding the drill steel up against the cutting face to blast out the horizontal hole big enough to get the tunnel boring machine in. So we basically would drill it out with about 100 drill holes and then pack it with dynamite and blow it out and then muck it out and then start the process over again, put in roof bolts and then move forward.
Holy smokes. Yeah, what was the point? Why were they building these?
It was a long-term water supply project for Prince George's County that had to run from the Potomac River through Montgomery County into Prince George's County, which is also a suburb of Washington, D.C. So it was basically for putting in a large water pipe.
Wow, feeding a city that didn't get natural water very well.
Yeah. Well, the Potomac River is the primary source. There are a couple large reservoirs in D.C., but there are some water intakes at Great Falls that pull water up and utilize it. Now, I didn't stay to complete the project. I decided after a year of that I was either going to be killed or become the operator of the tunnel boring machine and never see the light of day.
Oh my gosh!
And that I had an interesting experience there. I mean, it was a small job. And so I got to do basically everything, and it was great. But we were one of the deciding events to go on back to school and finish my degree was the tunnel boring machine had a catwalk on it, and the catwalk had popped off the machine and jammed into the wall, and it had bent the catwalk on the machine. Mm-hmm. And so me and the foreman were down there with a pry bar. And come along and a bunch of sledgehammers beating this thing, senseless when we both got knocked to the ground, and all the power in the tunnel was killed. And I remember kind of waking up foggy with water running into my pant leg and out my neck. I just remember that part. And we stood up, and you could look down the tunnel to the shaft. There was about 100-foot deep hole, lowered us down to get us down below grade and that. And I looked down the tunnel, and I could see a light at the end of the tunnel, but I didn't know if it was the light at the end of the tunnel or just the light at the end of the tunnel. And we came out, and it turns out that the transformer that was running the tunnel boring machine had been hit by lightning with a thunderstorm and came into the tunnel and amazingly didn't kill us. And but there was enough, we had iron rails and compressed air and electric lines and
kind of absorbed all the hit.
Well, yeah, I guess, and brought it our way, but I guess it had dissipated enough because we were about 500 feet down the tunnel, when the lightning hit. So they let us take another hour off. It basically was about 10 o'clock in the morning. So they let us come out of the tunnel, and basically we sat around, ate lunch, and then they put us back in the tunnel at 1 o'clock, and we were back to work.
Gosh!
At that point, I figured I probably should go back to school. So,
what an experience, man!
It was an excellent experience.
Holy cow, man! That sounds intense. It knocked you unconscious.
Well, I don't think we were out very long, if so, but I remember being knocked to the ground. Sure. And we're standing in a couple inches of water.
Gosh,
and holding onto a 6-foot pry bar. So it's amazing what you'll do when you're young and dumb and don't think you can't be killed by anything short of kryptonite. And then you get a little smarter.
Gosh, well, you'd think the company and the experienced guys running that ship would be like, hey, we got lightning in the area. Let's shut this thing down until the afternoon.
You would think.
Protocols.
You're back in the tunnel. It's safe, Of course, you look at everything, all the services, electric lines, compressed air line, compressed water line, the fencing that basically is used for roof control. The railroad tracks that we were running muck out of the tunnel with, So yeah, there's plenty of metal to bring power in, but I guess it had dissipated enough that it
didn't wipe you out.
No,
Son of a gun. Glad. I'm happy to have you.
Yeah, there have been a number of attempts over the years of my smiting, but so far they've been unsuccessful. So
you are resilient.
Resilient, yeah. I do get smarter with age, though.
Oh, man.
Some people would argue that point.
Well, shoot. So now you go back to, you're in grad school, or you go to a PhD program after that?
No, actually, I don't have a PhD.
Okay.
I had two choices: was to go the academic route, because at that point, if you went and got a PhD, you probably were going to do research and/or academics.
Yeah.
I was more interested in applied, practical work, and so I stopped at the end of my master's, and then became more of an applied hydrogeologist, and that. So after leaving, so it's really interesting. While in graduate school, I did my research on groundwater contamination with bacterial enteric contamination of groundwater systems in these karst settings and that, and also worked at the National Park Service at Mammoth Cave National Park, where I worked with a team of 3 or 4 other people mapping caves. And so during the summer, we would space our time such that we would be doing these 24-hour-long wetsuit trips into parts of the cave system that fed Mammoth Cave out on the Pennyroyal Plain, in the Sinkhole Plain, basically. So one of the caves that we would do would be what's called Wigpissel. It was about 20 miles of map passage at the time, and we were continuing to explore it. And the first 3,000 feet of the cave were basically hands and knees and or belly crawl in a stream, with 3 places that had about 6 inches of airspace, and we would push through and then get out of that feeder passage basically and into parts of the main cave. And so we would do these 24-hour-long wetsuit trips into the cave and map, literally miles of virgin cave. We walked down, some of the largest passages in the Mammoth Cave area were in this cave. But
were you walking this like the first people to walk?
Oh
this?
Yeah, absolutely. Yeah, we were mapping in this.
That must have been pretty cool.
Putting the first footsteps down.
Wow.
And that cave has now been tied into 2 other caves, but still hasn't been tied into the main Mammoth Cave system. And I think it's now about 26, 27 miles of map passage, including a couple major streams that are found in the cave. That's what we were interested in, is trying to map and understand the network of caves that feed the Mammoth Cave area. And so we were doing cave mapping. We would do a 24-hour trip, come out, go in, 8 or 9 o'clock one morning, come out 8 or 9 o'clock the next morning, and then we would go, get fed and go wash our clothes, get a day's sleep, and then maybe the next day or the day after we go back in, if the weather was stable. If the weather was not stable, we didn't go.
Meaning like it's not going to rain, right?
Yeah, right, yeah.
I mean, I can't do it. I don't know what kind of advice you have for me, but I just do not like being in caves.
Well, that's probably a pretty good advice, in the sense that maybe you're trying to tell yourself something. If you're not comfortable, that's okay. I understand that 100%. And as I get older, I'm not as comfortable with doing the crazy things that we did when I was in grad school. But we'd come out of the cave at 7 or 8 in the morning, and you have that 3,000 feet of crawlway that you have to go back through. And the problem is you don't know what the weather's doing outside. Hopefully, your weather reports were good and the weather was stable and that. But we would basically charge our car by lamps, and then we would just basically move continuously through that 3,000 feet until we got out of the cave. After 3,000 feet, you could get up into what we call a big dome pit, and that area probably didn't flood to the ceiling. But there were times when we would go in and we'd have a big storm come through, and we'd go in a couple days later after the weather had settled and that, and parts of that 3,000 feet had been rearranged, and there were tires jammed up into the cracks in the ceiling, and rocks moved, and that part of the cave obviously flooded to the ceiling. There's grass and stuff stuck to the ceiling that wasn't there before. So
wow. Man, why do they call it the Mammoth Cave System? Is it just because it's big?
It's the longest map cave in the world. It's now 420 miles of map passage. And there's some unique geology that comes together there. The cave itself is underneath the Chester Upland, which is basically Pennsylvania capped ridges with about 300 to 500 feet of limestone underneath it.
Wow.
And as the Green River cut down, it drained the levels over millions of years. So I think there's 5 different recognized levels. And the cave is, again, the longest known cave in the world. And there's another cave that's over 120 miles of map passage that's within 1,000 feet, I think, of connecting to Mammoth Cave, which will push it probably over 500 miles at some point.
Oh, my gosh.
Yeah, so, and it's been actively explored since the 1950s, mid-50s, by the Cave Research Foundation and, of course, by National Park Service teams and that. Those teams are no longer active. I basically caught the last 3 years of those, and after I left, the program was basically shut down.
Wow. What was the reasoning for that?
Well, funding, and then the park geologist, Jim Quinlan, basically left the park, and their research programs were modified and changed. They went more into sampling than that, and that he did over 500 dye traces in the Mammoth Cave area and developed a lot of the dye tracing techniques that we use today. And then
dye traces?
Yeah, dye tracing. Yeah.
What are you doing with that?
It's an expertise. It's fairly unique, I guess. There's not a lot of people doing it. A handful of people in the country that are doing it on kind of a professional basis. There are certainly more on the academic level that are doing it for research purposes. But basically, you're using a fluorescent dye is what we use. Uranine, also known as fluorescein, sodium fluorescein, or sulfur rhodamine B, or eosine, or one of the other dyes. And you can inject it into a sinkhole or a swallow hole or a stream or a well even. And what it will do is tell you a couple things. If you design the test correctly, and you're monitoring the correct areas, and that you would detect the dye, and it would tell you the connections, subsurface connection routes. It would also tell you the time of travel, how long it took for the dye to get from point A to point B.
Because it degrades or something? It changes?
Yeah, it can. But generally the dyes are fairly. They usually don't chemically change much in the water system. But again, it depends on how long they're in the system. And you can use this data to also determine concentrations or make estimates on what concentrations you would expect to receive if you do a quantitative trace. So we used to collect water samples, and also we would use active granular activated charcoal. And we may put anywhere from 30 to 50 or 60 of these charcoal traps out, and then go collect them, every couple days to every week or every 2 weeks, depending on what your design interest is. You pull them out, and then you extract the dye out of the charcoal, or you can run a raw water sample, because when you pick up the charcoal packets, you take a water sample at the same time. And then you can run them through a luminescent spectrometer, and then you can separate out the dyes and then look at the concentrations and that. And that's an expertise I've been fortunate enough to work with Dr. Quinlan and Dr. Crawford, who both developed a lot of the early techniques and have carried it forward. So that's
pretty interesting stuff. They're using light to see the differences in the water, the elemental differences in the water?
You actually use a scanning, synchronous scanning instrument that scans between about 450 and 600 nanometers. And you will offset those so there's the excitation emission wavelengths, and then you look at those, and you can detect the dye presence or absence.
Wow!
So you can use up to 5 dyes at a time. So you figure the labor to pick up all the bugs, or the charcoal packets and that are fairly extensive. So you do as many dye traces at the same time as you can, because you can separate out the dyes.
Now, this cave system, you think it's is it epigenetic or hypogenic? What is the difference?
Well, the Mammoth Cave system is epigenic. It basically is pulling water off of shales, less permeable rocks to the east, as that water basically is, as the small creeks and streams cross onto the limestone, it sinks into the ground underneath the sinkhole plain that's located basically in the Mammoth Cave area, but those carbonates extend from basically Bowling Green, Kentucky, north almost to Louisville, Kentucky. And then it flows underneath the Chester Upland, which is, again, Pennsylvania-capped sandstones. But that's where the body of the Mammoth Cave is. Most of it is underneath those the Pennsylvania cap rock, and it protects the cave from being eroded. So the escarpment is basically being eroded south over geologic time. Eroded west over geologic time, and will ultimately, probably destroy the caves.
Wow.
20, 30, 50 million years, who knows?
Wow. So it's eating its way from the east to the west.
Right.
Yeah. Oh, interesting.
Yeah.
And no evidence that this cave was made from below, made from a deeper.
There is a little bit of as the glaciers melted to the north and fed water into the streams, the Green River in particular, it cut down down into the bedrock about 60 feet lower than it currently is. And as the glaciers basically disappeared, the backfilling of the sediment, and so the deepest levels of Mammoth Cave are actually about 60 feet to 70 feet below current water table, the current level of the Green River. And so the springs that this water discharges out of come up from depth. And so some of those springs, like Turnhole Bend Spring, comes up vertically upward. And
from a big fracture system?
It's a conduit. People have dove some of those springs. I don't think they've actually been able to dive into Turnhole Bend because there's a lot of sediment that's slumped into the spring. But they've dove into Echo Spring and a couple of the others along the Green River, and been able to map them and actually connect them to parts of the system. Of course, we know they're connected through dye tracing too.
What is that?
So we know the springs are connected to the rest of the system, through tracer testing, through the use of dyes and that. So we know what conduits are basically connected to what springs, how quickly they'll respond to rain events. And this data is important because we have major transportation corridors that pass across the Pennyroyal Plain, the sinkhole plain. So we have a interstate corridor and rail traffic. And so the concern would be if there was a release of hazardous materials along that transportation corridor or through gas stations that are located on cities like Horse Cave, Cave City, and Park City, that gasoline could migrate into Mammoth Cave in a matter of hours to days.
Wow.
Yeah.
Sheesh. And is there like some geophysical tool or some way to kind of map this system from above?
Again, it depends on, there are attempts to do that, and sometimes they're successful. There's a number of different geophysical methods that people use. Ground penetrating radar doesn't seem to work very well up in the Mammoth Cave area because of the clay content, because there are relatively thick soils of clay. I have spent money to try and detect them using seismic, which was unsuccessful. And also terrain conductivity. One technique that we did see that seemed to work fairly well was called natural potential. And it's a fairly unusual method, but it looks at the streaming potential of water moving and air moving through conduits and that. And that seemed to work pretty well when we actually did a blind study with some geophysicists and said, run a transect, tell me if there's a cave there, and if so, where. And they were able to detect it with NP, but not the other techniques they used over top of it.
Fascinating.
Yeah.
So the model of how the Mammoth Caves and this whole system has come about is that after the Pennsylvanian, there's this big body of limestone that gets made
In the Mississippian
The
limestones.
Mississippi
actually.
lime.
Right,
The
Mississippi
famous
limestones.
Mississippi lime, all the way out in Kentucky. 600 feet thick, huh?
Approximately, yeah.
Holy shit.
Yeah.
Permian Basin's got like 100 feet of that. But anyway, it's associated with a world-class, reservoir.
Right.
Okay, and then that lime comes in, and then you have the change into the Pennsylvanian after that.
Which is all mostly clastics.
Okay.
There's a little bit of limestone in there, but mostly it's
Okay.
clastics.
And then at what point does that model kind of lithify or become, competent rock, limestone, and start eroding away?
Right.
And the idea is from above, that the rainfall and glacier melt and all that stuff, water from above is getting through cracks, joints, fractures.
Bedding plane partings. And then basically the acidified rainfall, basically the water picks up carbon dioxide, which forms carbonic acid, and it's a weak acid given enough geologic time and the right geology of enough rain, relatively thick limestones, potential head from the sinkhole plain down towards the Green River, the dip of the rock, etc. But surprisingly, there's very little faulting in the Mammoth Cave area, and the faults do not seem to control the cave. There are other more continuous things like bedding plane partings and some fractures in places, but the Mammoth Cave area isn't controlled much by fractures or faults. And that, and of course, the bedding plane partings are continuous. From the sinkhole plain, they go down dip to the Green River, which also helped enhance the formation of the cave. And then over geologic time, over geologic time, the aggressive water basically has removed, the limestone and created these, massive conduits that you can now walk through and are part of the longest cave in the world.
Now, do you think that during that whole model, the natural springs and the way the water's coming up, the fractures from around the caves, like you talked about, these conduits,
Yeah.
that are bringing in the water from deeper, do you think that was running the whole time?
Well, it looks like the levels of the cave are related to terrace deposits out on the surface, and so the Green River probably controlled the active level of formation of the cave. And as the river has cut down over geologic time, deeper layers, the conduits in the deeper part were basically eroded out, dissolved, and activated. And so it probably was more of a top-down. The higher levels were formed first, the next lower levels were formed next, et cetera. And currently the active levels right now, you can actually go into parts of Mammoth Cave and see the stream. They used to do actually tourist boat rides on the Echo River. And so of course, us as cavers, we walk through some of those streams and places, and mapping the caves.
And the bottom of the cave right now sits on top of the Pennsylvanian.
Yeah, it sits on, I believe it's Mississippi now. You're talking 30 years since I've worked up there.
Yeah.
So they're sitting on a less permeable, I think it's the Salem-Warsaw Formation.
It's Mississippi, not Devonian. It's not.
I think, if I remember right, it's Mississippian. It's lower Mississippian.
Yeah.
Yeah.
Wow.
And that, so.
Man, okay, that's really interesting stuff. Really interesting. The cave systems are massive. I can't believe that. And there's a good map of that.
Yes, yeah, absolutely.
So you got like GPS data points of the crews that are like walking and mapping these.
Well, GPS doesn't work in the cave. Yeah. So the entrances are tied in usually with a very high quality, like theodolite survey from a known benchmark. So the quality of the survey is actually very high. And the mapping process that we use in caves is basically a high precision compass like a Brunton or a Sunto that you can read down to about 1/2 degree. And then a clinometer, so you can look at the angle, so vertical angle, and then a tape. And so commonly use a steel tape, or you use a fiberglass tape, and you go from point to point to point, or what we call station to station to station.
Yeah. Wow.
And at the same time, you're doing a sketch in your field book. And so you're noting, the width of the passage, the height of the passage, whether you're in a stream, any other, sediments, anything else that you might see, formations, biology, archaeology, et cetera. And there are places in Mammoth Cave where, there are bare Indian footprints from 3,000 years ago with sandals, parts of sandals and fragments. Mammoth Cave was, known by the Native Americans and was utilized, and they went miles back into the cave. There are cane torches that have been left in the cave, and occasional people. So
wow, you're looking at the folks back in the cave days.
Yeah. And my very first cave was Mammoth Cave. When I was 12 years old, we went down to visit my uncle.
Okay.
And he took us to Mammoth Cave, and in the early 70s, I guess, probably late 60s, and got to tour the cave. And of course, at that point, I was hooked. So
sounds like it.
Yeah.
Wow.
So,
right on. Okay. So you spend most of your career then doing hydrology, groundwater, cave mapping.
Yeah. Well, after I graduated from Western Kentucky University and was working for the National Park Service and that, the state of Kentucky was given a grant by US EPA to create a groundwater program. And I was actually hired to manage that program, create that program management. So I was the first employee for the groundwater section in the state of Kentucky's Division of Water. Did the hiring of all the new staff. I think part of it was because at that time, most people who were studying geology at the master's level were going into oil and gas, and I was one of the few people who was interested in hydro.
Sure.
And matter of fact, I think I'm one of the few people that probably is still working out of my undergraduate class in geology. Most of because come the early to mid 80s, there was this huge downturn in the oil and gas industry, and most of those folks were laid off and had to reinvent themselves as either environmental geologists or computer programmers or whatever they could find. So I went and managed the Kentucky Division of Water, wrote the groundwater management plan for the state, and got to testify in front of the state legislature a couple times.
I was just thinking about that.
And really interesting career move. But after 3.5 years of basically being a regulator and developing regulations for water well drilling in the state of Kentucky,
no kidding.
That was under us. We had no regulations or at that time anybody could drill a hole in Kentucky. And that was a very interesting, was taking a bunch of drillers and requiring that they get licensed and to drill wells under. But it was really interesting because we served, we created a thing called the Water Well Drillers Advisory Board, and I basically was the staff person for that. And we brought in water well drillers from around the state, folks we recognize as being experts in the field, master water well drillers, et cetera. And we spent 2 years basically going through every type of drilling condition that you would find in the state of Kentucky. And so it was a PhD level education from a bunch of water well drillers who spent literally days and days and days going over how a well is drilled in Eastern Kentucky versus the Jackson Purchase in Western Kentucky versus
different things they run into.
Every one of them, everything from cable tool, air rotary, to auger rigs, et cetera, bucket rigs as they call them. And so it was an excellent education working with some incredibly fine drillers.
Wow. A friend of ours is a hydrologist for one of the big consulting companies in Fort Worth, and doing that she basically writes all the reports of, like, here's a neighborhood of 2,000 homes, how many wells are they going to need drilled, the whole concept of feeding fresh water, getting fresh water from shallow crust to the processing plants and to people's homes. And what a interesting idea. Where do you? So I had some experience in my undergrad. I got to go to the Oroville Dam in California, and I got to sit in on the legislations of the farming community saying this is our water, the cities of Southern California saying, we don't have any water, we need your water for our city. And then you got just on top of that, I guess the people who just live there and want to use the water. How do they manage that, and how are they traveling that water? How is it all? How are you being fair about all that? And then you got to worry about the fish. There was a massive fish problem because these things are swimming around, and you're trying to divert that, and it's not going well. You're messing up fish population. So it was a super complex, and the history was amazing. I mean, when they started building those the aqueducts, man, the people that lived along those aqueducts were shooting the construction workers and shit. Like, this is my water. What are you doing? They didn't understand what was going on, and they're like, hey, this might. I can't even imagine. So what they did to salvage a lot of those people, they get like super crazy discount on their water. Yeah. So that's how they do that.
The Western water law and Western water wars are quite interesting. And that, but it was interesting because I worked 3.5 years for the state of Kentucky, and it was a great experience. I was very fortunate to work under two, wonderful mentors, Bob Ware and Don Harker, and they really helped develop my career. But after 3.5 years, I wanted to actually get more hands-on experience, so I left and went to work for a company called ATEC Associates, which was an environmental and geotechnical engineering firm. I went down and set up their program in Nashville, Tennessee. So I went from Frankfort, Kentucky to Nashville, Tennessee, and there we did sinkhole collapse issues, which I'd had some experience with already, living in the Bowling Green area and working in Kentucky. And I got to work on a number of environmental problems in Kentucky while I was there with the Division of Water. Lots of PCB issues associated with discharges into sinkholes and the subsurface and that. But I wanted to get more hands-on, so I left and went to ATEC, where we basically, it was the early days. This was, I guess, 1986. I went to 1986 and went to ATEC Associates, where we did a lot of underground storage tank and landfill work. And I ran their environmental programs for 3.5 years. And then at that point, took another position with a company called Eckenfelder, which was also in Nashville. And that group did large environmental projects. So basically, I ended up being a program manager and director of their karst hydrology program, and basically managed Superfund sites, large NPL sites, National Priority List sites. So I worked on projects all over the East Coast, and chased a lot of contaminant.
Wow.
Probably the most notable project was, I had a couple of them. There was some large chemical industries in the Paducah area where we did their RCRA monitoring, their Resource Conservation Recovery Act monitoring, and their quarterly monitoring, where we sampled, probably 30 or 40 monitoring wells in a place where they made CFCs.
CFC.
Basically their equivalent to Freon. It was refrigerants, and they also made a number of other things there. They made lindane, which is a pesticide, or at one time did. They also made, they had a process where they would use mercury to pull chlorine gas out of brines.
Wait, pull the what out of the brine?
Pour chlorine, so they would take chlorine.
Chlorine out of the brine.
Yeah, so high concentration salt brines, and they would use this process where they would use a mercury cell to pull the chlorine out.
Wow,
and then
what?
That would feed into their stocks for their other processes that were going on there.
Wow.
They also made roofing tiles there because the fluorinated hydrocarbons are basically fairly inert. And now they're turning out to be these, what they call them forever compounds, the PFAS compounds. So this is one of the plants that made it. And they used to take fluorite from the fluorspar mines over in Cairo, Illinois, and bring it into the plant, roast it, and make hydrofluoric acid, which is fairly aggressive, as you might imagine.
Yeah.
And then they would take that and mix it with a carbon tetrachloride and make fluorinated carbon compounds.
Fluorinated carbon compounds.
Yeah. So basically, refrigerants.
What the?
Well, one thing I'd like to go back and talk about is you talked about geophysics, and there was a effort at Mammoth Cave National Park to install some monitoring wells into some of the conduits, the large cave passages that have water moving in them. So Dr. Quinlan had obtained some grant money to drill some wells, but considering the length of distance from the entrance to the locations that he was interested in having these drilled, which might be miles, a small error in the compass reading could throw the location on the surface where you wanted to drill off by hundreds of feet. And so there is a geophysical technique called a cave radio that we use to pinpoint our location on the surface.
Wow.
So it was a transmitter and a receiver, and the transmitter was a coil of wire about 2.5 feet in diameter that was mounted on a piece of plywood that we had to carry way back into this cave. And then you have to lay it exactly horizontal, and it creates this wave. Basically, it looks like a donut. And then there's someone on the surface with a similar coil that's tuned to the same frequency.
Wow.
And they walk over the surface until they don't get a signal. And when you don't get a signal, you're exactly on top of it.
Aha.
And then you can move back, let's say 100 feet, and you can tip the coil so that it's parallel to the waves that are being created, and you get a null signal also, so you now know the angle. So you can use simple trig to basically calculate how deep to drill. And so we had to do a number of these. Two of them were over 450 feet deep, and we drilled directly into the passage using this. The passage was 20 to 30 feet wide, 5 to 10 feet high.
Nailed it.
Nailed it. Now, there was some that we drilled that were not, they made it into the passage, but not right into the middle of the passage. And so myself and another fellow had to go into the cave and basically cut a hole in the PVC casing so that we could then run the instrumentation out and put it in the middle of the stream and that. So we went into the cave, a multi-mile long trip, many hours carrying all kinds of equipment. We also drilled a new entrance into the cave, and that one we located again with a cave radio, and it was only about 55 feet below the surface to the room that we were drilling into. And we drilled a series of different sized bits. I think the pilot hole of like 6 inches to make sure that we got into it, and then I think the next bit was 17.5 inches, and it drilled all the way into the hole.
Holy smokes.
And then we came in with another bit that was about 26 inches.
Holy smokes.
And the problem is that Jim was trying to save money, and so he bought a used large diameter drill bit, and about 25 feet down he twisted off basically the drill cones, and they dropped down into the cave, and so we had to go get them. And to get into the cave required a 125-foot rappel, and then hours of crawling and walking and crawling and swimming and to get to the place where this entrance was.
Yeesh.
And so we got to the bottom of the entrance. We could look up, and 55 feet to the surface. And we put the broken off drill cones, I guess, the roller bit, into a bag, and the guys hauled it off of the surface and that. And then Jim lowered down 2 personal pan pizzas and 2 beers, and we had lunch there, which was quite a treat, a surprise. And then it was real interesting because the guy I was with had been involved with the exploration of the end of the stream passage upstream on what's called the Hawkins-Logsdon River. And he had poked around in this breakdown pile with some other folks and think he found a way on through and made, in essence, what was the connection between Roppel Cave, which was about 75 miles long at the time, and Mammoth Cave, which was about, I think, 290 miles long at the time, Map Passage. The connection was actually made a few months later by some people that went into two different entrances and met in the middle and surveyed and tied the two caves together. So we were coming in about 2 months later, 3 months later. This was, I think it was November. And Chris said, well, I think we should go out a different entrance. And I said, well, the entrance out the Proctor Cave, entrance was, had, the ropes weren't rigged. And so you couldn't ascend from the bottom. You had to come in from the top. And the entrance out, what's called the Ferguson entrance, wasn't rigged either. That's a 55-foot climb out, and so we couldn't go out that way. And so Chris said, no, I think I'd like to go out Roppel, which was about a 6-mile trip out.
Jeez.
So we got, so I said, well, okay. So we went upstream, crawled through the breakdown pile where Chris crawled, popped out through the breakdown to a stream that was coming downstream, which was the upstream portion of the Logsdon River. And we walked and crawled and swam. Of course, we didn't have wetsuits on, so this was pretty crazy. The initial connection, which didn't go in the entrances we went in, that went in much closer entrances to the connection net, carried in wetsuits. So Chris and I were wading in chest-deep water and swimming in a few places, and then came to what's called the S-163 sump in Roppel Cave, which had about 4 inches of airspace.
Oh my
And
gosh.
we pushed on through that and came up in Roppel Cave. Of course, I managed to hit my shin on a piece of rock that was under the water and laid a big hole in it, and it was bleeding and that. We got there and got a first aid kit, got it stopped.
Jeez.
And then we crawled out the Roppel entrance, which had a gate you could open from the inside. And we got out about 11 o'clock at night, and it was about 36 and misty.
Oh my!
And we had to walk about 5 miles back.
Oh my gosh!
So we were walking down the dirt road, and this car comes down the road, and it turns out that I knew the guy who he lived in the farm there right by the cave, and he said, we asked him if he could give us a ride back. He said, sure, get in. And of course, we're just covered with mud. And we said, no, why don't you get your truck and we'll just, and he goes, okay. So he parks his car, gets his truck, comes and gets us, and we drive about a mile down the road, and the car runs out of gas.
Oh my God.
It's about midnight now, and he goes and beats on this door, and somebody comes to the door with a shotgun, and the guy comes out, and he calls his wife, who gets the kids up and gets in the car and drives us over to our car about, again, by road, it was probably about 10 miles away. And we gave him like $20, which was for a ride. We drove back, and Jim was excited because we were way overdue and nobody knew where we were. Yeah. And it was pretty gonzo cave trip. And I told him, I said, Jim, we got really lost coming out. He goes, oh my God. And I said, we walked around for hours until we found this other entrance. And we said, we better get out while the getting out was good. So we came out this other entrance. He goes, oh my gosh, what cave entrance was it? And I said, well, it was the Roppel entrance. He goes, oh, you connected the caves, didn't you? He goes, yeah. He said, well, I'm going to dock you pay. How much was that? And it's like, I don't know, a couple hours, So he supposedly docked our pay 3 hours or something. But
what?
Yeah, Chris and I, made just by ourselves out there, miles and miles away from where anybody would have ever looked for us.
Yeah.
But we were probably some of the best cavers in the country at the time.
Wow.
And we were caving 2 to 3 times a week, doing very long trips and hard trips and vertical trips and that.
Super unique
Yeah.
experience.
So after that, they were drilling the 2 wells into the cave, and one of the drill bits jammed in the hole. And so this was again late in the year, and I had to go in and basically see if we could fix that. So from inside the cave, which I wasn't optimistic about. So I was the only one who was available at the time. All the other cavers who were working in the summer basically gone back to school and respective places and that. And so I called up George Venny, who was a graduate student at Western, to see if he would go with me in that. And Jim at the time was in getting a quadruple bypass. And so he said, do whatever you got to do. And he got us all lined up. We carried in 2 duffel bags full of tubing and hoses and 10 pounds of what I'll call Dr. Nobel's Instacave, if you know what I mean. And we went in and built a ladder. The drill bit was sticking out of the ceiling of the cave, and I think they left it overnight when they punched into the cave. And then some material had fell in and jammed and kept them from pulling the drill bit out.
Yeah.
And so we basically built a wooden ladder and ran it up against the drill bit and inserted about 10 pounds of Tovex, which is a type of explosive, up around to see if we could shake the drill bit loose. And George and I ran the wire down the passage to a breakdown pile and got up on the breakdown pile. And George insisted that we move higher up on the breakdown pile. And it's like, well, okay, I guess, And we touched it off with our wheat lamps, these electric lights that we were using. And it was basically like a air burst, and it knocked us both to the ground.
Damn it.
And we laid there, laughed, and once our hearing came back, and this big wave of water came down and splashes up onto the breakdown pile and rushes back down the passage, from the blast wave, and it didn't do anything at all to the drill bit. Yeah. So George and I were coming out of the cave, and we actually went into the drilled entrance, what's called the Doyle Valley entrance, that was still only 17 and a half inches in diameter. And so I had rigged up a system where we could get lowered in and get hauled out from the surface, and that with a mechanical advantage system in that. And so the problem is it was about 5 degrees out on the surface, and they'd left the lid of the cave entrance, this drill hole, off. And so this cave was just sucking in all this cold air.
Shoot.
So when we got into the room, the cave being 56 degrees and 100% humidity, it just turned into fog. And so as we walk into the room, you couldn't see your feet on the floor. And we couldn't find the hole. And so I finally got on our hands and knees, because you can't really see where you're walking. We crawled around the left side of the wall, because I knew that entrance was around there somewhere, came to the flowstone mound and went up the flowstone mound to the bottom of the entrance, which was clear. You could see that because it was just cold air rushing in.
Jeez.
Hooked onto the rope. The guys on the surface pulled us out. We're in wetsuits covered with mud and exhausted in that. And the driller was there, and he thanked us in that. We went back in later doing the exact same thing. He had managed to get the drill bit loose, but the actual drill cone had come off. The drill bit had come off, fell in the cave.
Yeah.
So he ran a cable down the drill hole. We ran it through the drill bit, put a couple cable clamps on it, and he pulled it back to the surface. So then we come out of the cave. It took us 3 or 4 hours to get out of the cave. We get pulled out of the surface and that. And he's there, and he says, we're peeling out of our wetsuits and things, and he says, "Hey, you boys look like you could use some hamburgers. Here's $100." And there was
you saved him $20,000.
Oh, probably, yeah. And that. So about 6 months later, I get this job working for the state of Kentucky, and it turns out the water well drillers.
Same guy.
Same guy. He comes in and goes, last time I saw you, you were in a rubber suit. And we developed a great friendship, and he was a great mentor and friend, and taught me a great deal about the nuances of drilling wells in karst. So crazy days working for the park,
Man.
It's amazing what you'll do for $4.25 an hour. Graduate students are expendable.
Well, especially when you're having fun.
That's when you're having fun. I couldn't believe getting paid $4.25 an hour just to map Virgin Cave, and occasional drill bits, and maybe getting blown up, but other than that. So
wow.
We managed to get the drill bit and got the wells fixed and things. So
wow.
That was crazy.
Yeah, it is. Well, we'll start the drill down segment of the PBE podcast, and this is going to be let's teach me a little bit of the difference. You get 2 kind of fundamentally different caves that get made.
Okay.
The top down system, right, and then the bottom up system. So
there's a great deal of work that's been done in classifying groundwater systems in karst. The 2 primary ones that people are most familiar with are the epigenic processes, which is bottom down. So rain falls, it coalesces, it goes into a sinkhole, goes into a conduit, flows underground with rapid groundwater velocities of as much as a mile per day or more, and discharges at a spring. And those are what you see commonly in the central U.S., the Mammoth Cave area, that Mississippian limestone that and in Kentucky, and also the Cumberland Plateau and many of the other caves in Tennessee area, and also in West Virginia and some of the other major caving areas and that. So it's not uncommon to be able to walk along some of these conduits. And the advantage to it is mapping caves is it allows you to see the fabric of the aquifer. It's one of the few places, because if you think about traditional groundwater, it's really a remote sensing science, because you don't get to see the aquifer. You get to sense it through a well, through instrumentation. You might be able to shine a light down the well and see the top of the water surface and that. But in reality, we collect data out of these wells. We do aquifer tests, et cetera, and that. But to actually, we may be able to pull up a core, we may be able to pull up cuttings, et cetera. So you get a very small view of a very large aquifer. In these karst systems, we can sometimes enter them, and you can map out and look at what is the controlling the fabric of the aquifer. Are we looking at bedding plane partings? Are we looking at fractures? Are we what faults? What roles do all those play in controlling groundwater? And so in some of these systems like the Mammoth Cave, there are places where you can walk for literally miles along these underground streams, and you can also do dye tracing, which allows you to understand, again, the groundwater velocities, which are important for spill response and hazardous materials, and also interconnectedness to either springs and or public water supply wells, as well as domestic wells. In the last 20 years or so, there has been more interest, I should say, in looking at systems that may be confined that are still karst, and probably the best example of that would be the Edwards Aquifer here in San Antonio. And we have been able to look at some of the caves in this area that are old paleo springs, that you can go into and look at them and try and understand their mechanism of formation, what's controlling the major flow paths, the conduits and that. But in dealing with a system like the Edwards Aquifer, which is very deep in many places, where wells are drilled that are over 1,000 feet deep, to pull up water, and in some places the aquifer is as much as 3,000 feet deep.
Wow!
And still fresh water.
Wow!
How is that different from these epigenic systems? And I've been looking at these things because to be able to transmit huge volumes of water through the aquifer rapidly, to be able to get large springs like Comel Springs and San Marcos Springs and Goodenough Springs and San Felipe Springs and Barton Springs, these are major discharge points. If you look at the type locality, temperate karst area, Mammoth Cave being an example, the largest springs in that area may be 1 cubic meter per second discharge, and maybe a little bit bigger during storm events and that. The discharge at Comel Springs ranges from 5 to 10 cubic meters per second. So these are massive springs. So these springs must have large catchment areas. Especially since you're looking at the difference of rainfall in the Mammoth Cave areas, let's say 45 inches, whereas here is 26 to 30 inches maybe, or 22 inches farther west. These must be massive catchment systems.
How are you saying that? What's the word you're using?
A catchment.
How do you spell that?
CATCH, catchment. The contributing zone for the aquifer. So the watershed that feeds and recharges water to the aquifer and the aquifer system itself must be very large.
Okay. And it's not coming from above here.
Well, it has to somewhere. And so what you get are these regional systems like the Edwards, where you have rainfall falling on the Edwards Plateau to the north of San Antonio, and onto the hill country, which is the dissected Edwards Plateau. And as you move farther south, you intersect the Balcones Fault Zone, which pushes the Edwards limestone vertically downward below the surface. So as water comes off of the catchment, off the watershed, basically it flows south, and as it intersects the Edwards limestone, it sinks into the ground. Okay, in those areas, you have a water table, and there are some caves that we can go see the surface of the water table in. There are not too many, but there are some that allow you to basically go into the cave, work your way vertically downward, sometimes hundreds of feet, and actually see the surface of the water table of the Edwards Aquifer. But the faulting takes the Edwards farther, deeper as you go south. And so, for example, in Medina County, the Edwards limestone in southern Medina County may be 3,000 feet below the surface. Okay, wow. So you've got this Edwards limestone that's anywhere from about 450 to 1,000 feet thick, depending on where you're looking at, and it's fully saturated in what's called the artesian zone. Okay, so we can't physically go into those through cave diving or other techniques. Again, we're back to remote sensing the aquifer through wells. And so we would go in and we would map the potentiometric surface, the water level, how high water will rise in the wells above the artesian surface. And the top of the Edwards is confined from the Del Rio clay. So looking at the stratigraphy in that, we have the Glen Rose limestone below the Edwards limestone. We then have the Edwards limestone, which is the primary aquifer in the area. And then we have the Del Rio clay, which is basically this confining unit. That's about 40 to 60 feet thick.
Wow.
So the water is basically captured in between the Del Rio and the Glen Rose. And the water system has a hydraulic head to it with aquifer elevations higher in the western part of the system in, let's say, Uvalde County.
Okay.
And the discharge points, which are San Antonio and San Pedro Springs here in San Antonio, Comel Springs, which is in Comel County, and then San Marcos Springs in Hayes County.
Wow.
These are the discharge points for the aquifer. So the water system, the Comel Springs appears to come up along the Comel Springs Fault, and the artesian zone basically is at a depth of about 600 feet there. So water's coming vertically upward out of the Edwards limestone to discharge at Comel Springs.
Wow.
There also appears to be some contribution of the recharge zone, the area where the Edwards limestone is exposed on the surface at Comel, because that fault has about 800 feet of displacement along it.
Wow, the Balcones.
The
Comel.
The Comel Springs Fault does. Yeah, the Balcones Fault Zone has as much as 3,000 feet of displacement along certain faults. So it's a series of parallel or in echelon faults that go down to the south. Okay. So there's water flowing from the west, probably somewhere. There's a groundwater divide somewhere in the east of Brackettville, because there's Fort Clark Spring, and water flows down gradient towards Comel Springs and San Antonio, San Pedro, Comel, and San Marcos Springs, which are located to the east, and which is why these cities are where they are. So, Bexar County, sure. San Antonio was basically founded around these water supplies, San Pedro and San Antonio Springs. New Braunfels is located, at Comel Springs, and San Marcos Springs, is where San Marcos is. So, so why do these deep, complex carbonate systems, these karst systems, form at depth? Normally, you would think that as the water would flow in from the surface to recharge the aquifer, it absorbs carbonic acid, and then once it meets the Edwards limestone, at some point it basically is saturated. So how do you get deep conduit flow systems in the aquifer at 1,000 feet below the surface. And we know they're there because we see things like drill bit drops, and we see, significantly, some large, bedding plane partings and vulgular porosity in that through our well cams. So how do you get this? And we think that, I think, there are other people who will disagree with me. There are a couple things. You get a mixing corrosion issue when you take two waters that may be saturated, but you mix them together. What happens is the water becomes unsaturated and can absorb a little bit more calcium carbonate. That was shown through some work by Dr. Bogley, because the mixing of the waters is linear, but the curve for dissolution is asymptotic. So and so that's been well studied in that. So we think we have some mixing corrosion. But the other issue is that we see a high concentration of hydrogen sulfide in the wells that are down gradient of what's called the saline water freshwater interface, or what is also known as the bad water line. It appears that there are bacteria that live on the chemical gradient between the high saline water and the fresh water. And they take the sulfates and convert them to sulfides and outgas hydrogen sulfide.
Wow.
And when you mix that with fresh water, you form sulfuric acid.
Holy shit.
And so the bacteria, so the high porosities, which occur throughout the Edwards artesian zone, are probably created by this biologic component.
Wow.
Okay.
And
so
that's kind of on a line, huh? This contact,
contact, yeah. And we've mapped it roughly, pretty well refined mapping, and we used, I think it's 1,000 TDS, total dissolved solids. So anything less than 1,000 TDS is fresh water, and anything over that is saline water.
What else changes across that contrast?
So we found that the permeabilities that you see in the artesian zone are pretty consistent. You can drill a well almost anywhere in the Edwards, and you will only be physically limited by the size of your pump and the diameter of your hole. There are wells that yield 5,000 gallons a minute, which have virtually no drawdown.
Jeez.
Yeah, so the permeabilities are extremely high.
Yeah.
Okay. Whereas if you were drilling a well in one of the epigenic karst areas like Mammoth Cave, you might drill 100 wells and you might get 1 to 3 to 5 gallons per minute out of a particular well, unless you got lucky and hit one of the conduits. Dr. Quinlan used to make the analogy that hitting a conduit in the Mammoth Cave area, even though we've got 400 miles of map cave, would be like throwing a dart at the map of the United States and hitting the Mississippi River. You might do it, but chances are you're probably not.
Wow.
And so there are some wells that yield hundreds of gallons a minute in some of these areas. Most of them don't. And even in the recharge zone of the Edwards, most of the wells there yield a few gallons per minute. Okay. But down in the deep artesian zone, we see these incredibly high permeabilities. And I think what has happened is you have a positive feedback loop, and over geologic time, that saline water freshwater interface has migrated south and also east, down gradient. So 5 million years ago, the saline water zone was much closer to the recharge zone. And as the sulfuric acid process occurs, it creates a larger permeability, which increases the ability for more water to move through it, which increases the ability to dissolve out more rock. And so you get this positive feedback loop, and you start integrating these very large drainage networks.
Yeah,
and so what we think is happening is that these bacteria are basically feeding off this chemical gradient between the saline water and freshwater zone.
Yeah.
And they have developed a very well-developed ecology right there on the saline water-freshwater interface. So at depth, there are 2 different species of catfish that live in the aquifer that along the saline water-freshwater interface that have only been observed when they've been basically pulled out of wells and captured in nets.
There's catfish.
Catfish, yeah.
In the Edwards Aquifer.
Yeah, blind catfish. They're white. They have no eyes. They have no air bladder because they don't need one.
What?
And they're living fat and happy in the Edwards Aquifer. One of them has a sucker mouth and eats bacteria. The other one has teeth and is probably a predator. There are over 60 different species of animals that have been identified. The isopods, copepods, right? Shrimp.
Is that right?
Yeah,
in the aquifer.
In the aquifer, blind leeches, and to be able to have a parasite like a leech, you have to have something for it to live on. So we have a number of different salamander species that are found near the springs, but not in the deep wells. So there have been catfish pulled out of wells located over by the AT&T Spurs Center, the basketball arena, the fairgrounds. There are a couple large wells there that have
pulled catfish.
That had catfish come out of them.
The no-eyed ones or the teeth?
No-eyed ones. Well, all of them. The 2 catfish that live in the aquifer are both blind. They have no eyes. They don't have any need for them.
But one lives in the fresh.
No, they both live in the freshwater. All these critters live on the freshwater side, right on the edge of the saline water freshwater interface.
But one of them's feeding on that interface with the sucker fish is feeding on that interface.
Correct. Yeah.
What do you call this interface again? What's the name of it?
It's known locally as the bad water line, but we also call it the saline water freshwater interface. And it's generally
through geologic time, the idea is that it was higher, but now it's
migrated from north to south, and from west to east. So the aquifer curves, from San Antonio it basically goes northeast, but towards San Marcos, or from San Antonio it goes basically due west towards Uvalde. So there's kind of looks like a big banana.
Yeah, just like the Balcones zone.
The catfish are only known from Bexar County, pretty much, and maybe a little bit of Medina.
Wow.
They're very, very hard to sample because you have to put nets, to catch them.
Your water wells.
Right, and the problem is most of these water wells are not being used to recover catfish. They're being used for water supply. So they'll go out into an irrigation system or into a public water supply. The catfish are probably not very common, but we certainly have detected them. Now there are some techniques called environmental DNA, where you don't have to catch a catfish. All you have to do is catch some cells. And those techniques may be applied to better understand the extent of the presence of the catfish.
Yeah.
But sampling is extremely difficult just for catfish.
Can't imagine.
Yeah.
That's crazy.
Yeah.
That's really blowing my mind. Okay, and then we talked briefly about the style of cave system of the Guadalupe Mountains in the Permian Basin.
Correct.
This is now considered to be hypogenic.
Right.
Am I saying that right?
Right.
Hypogenic, meaning it's coming from below,
right,
and it ate away at the rocks from a down up.
And that's why you see in Carlsbad Caverns, and then also another cave that's even bigger called Lechuguilla Cave, which Carlsbad's about 26 miles, I think, of map passage, and Lechuguilla is over 100 miles.
Wow.
Lechuguilla was So Lechuguilla was discovered in the, I think, mid-'80s. So it's a relatively new discovery. Both of them appear to be driven by this sulfuric acid process. And the water levels have dropped over geologic time, and we can now enter those caves. And so the sulfuric acid process explains why there are massive gypsum deposits in places like Carlsbad and Lechuguilla. There's elemental sulfur in Lechuguilla Cave that's been identified. There are very weird, bizarre formations in both caves.
Bizarre how?
Gigantic gypsum chandeliers.
Is that right?
Some of them 10 to 15 feet long. They just stick out of the walls like daggers.
Is that right?
Yeah, they're amazing.
Wow.
Yeah. So, and so the cave's got also a number of other unique formations in it that are.
Wow. Have you heard about the Project Gnome in the Guadalupes, where they went and they set off a nuclear warhead?
Yeah, I've been to that site.
You have?
Yeah.
Man, I wouldn't want to be close to that. You don't think there's still radiation pinging off the walls?
Well, you can't go in it. Oh. It's just a marker on the surface.
Oh.
And then of course there's the WIP site nearby too.
What's that?
Waste Isolation Pilot Project, which is near Carlsbad for military high-level and mid-level military radioactive material.
Oh, whoa! They're pumping it into a hole?
No, they bring it in barrels and they basically put it into this salt deposit. If you ever get a chance, take a tour of it. It's fascinating.
Wow.
And you can go in there.
Big salt mine?
Yeah. Well, it's yes. They're mining salt, but it's mostly for
storage.
Yeah, for storage. Now there are nearby potash mines too, but
right.
But the WIP site is basically a long-term repository for radioactive material. A lot of it, I understand, is fairly low-level personal protective equipment and other stuff, but they have different levels, and some they'll stack in barrels and hallways, and then just let the salt flow over top of them. Others, they drill holes into the walls and slide the barrels in and then put a plug back over. So yeah, wow. I was fortunate enough to get a tour of that site once.
Wow. Very interesting.
Yeah, so the I'd been kind of looking at this data and scratching my head and trying to figure it out. But there was a gentleman that came in from Ukraine, Dr. Alexander Klimchuk, and I'd met him in the 80s when they were, before the fall of the Soviet Union. They came over and did a tour through with Derek Ford from Canada and toured part of the United States looking at cave and karst systems then. And Alexander had developed this process where he was evaluating some of the large gypsum caves in the Ukraine. Some of them, again, over 100 miles of map passage, and that set up on these high density networks of, basically looks like city blocks. So the cave density is extremely high. And these caves also seem to be formed by water ascending from formation below.
Wow.
And eating out along fractures and other things.
Yeah.
He came over and did a sabbatical with the National Cave and Karst Research Institute in Carlsbad, and I went over and was at a meeting, met with him again, and invited him to come here. And so he came and stayed at my house for about 2 weeks, and also did a lecture for us at the Edwards Aquifer Authority. And he was interested in these maze caves, and he said, Gary, I've looked at some of the maps, and I'd like to go visit these caves. So I said, fine. And one of the caves he wanted to visit was called Robber Baron, which is located here in San Antonio near the airport. Wow. And it's a cave that's set up along fractures in the Austin Chalk. And so we went in the cave, and Alexander was asking me what I thought about the formation of the cave. And I said, I think you're going to think I'm crazy, but I think it was formed by ascending water. And here's why. This is what I see in the cave that tells me that. And he runs around for a few minutes and says, you're exactly right, except you've missed one or two other features, and pointed those out. And once he points them out, they become real obvious.
To better explain the ascending.
Yeah, there are vents. There are small round holes where the water comes up. And so he got real excited. He said that cave is the best example of hypogene speleogenesis that he'd seen in the United States to date.
Wow.
So I said, okay. So he said, now I'd like to go to another cave called Amazing Maze Cave in West Texas. And it's about, I think it's 6 or 8 miles of map passage, again, set up on these fracture patterns.
Wow.
Extreme high density. And of course, we go in there and we find, I believe it was an indolite clay, which is a waxy kind of clay that forms from the breakdown from sulfuric acid of certain carbonates in that. And then he said, no, this is the best example I've seen of hypogene speleogenesis in the U.S. And then we went to caverns of Sonora,
Oh, yeah.
And took him in that cave, and he got very excited. And there's also some weird mineralogy there. Some vanadium, uranium sulfate minerals that are very unusual. Metatiaminite, I think is the word. And he thought that cave also, he said this cave is also formed by hydrogen sulfide and rising water from depth and that. And these caves are basically probably formed at the end of very long regional flow paths. So the water comes into the recharge zone, flows horizontally and probably some vertical gradient down depth, and then it comes to the discharge point and the water comes up. Okay, so you've got water in the recharge area goes down like we do at the Edwards. You have it flow into the artesian zone, and then it flows, vertically or horizontally over to discharge at Comel and San Marcos Springs, and that water there comes up from great depth. Okay.
Wow.
So the caves that we're looking at, like Amazing Maze, Robber Baron, the Caverns of Sonora, and 2 other caves that I took him to that are wild caves, are all formed by ascending water. And they have very unique characteristics to them that once you kind of train your eye to, you can pick them up. What we're seeing is some of the caves on the recharge zone in the Texas Hill Country appear to be hypogenic, but have now been abandoned as the water levels in the aquifer have dropped and the artesian system has migrated to the south. And so you're seeing these hypogenic features that are now being overprinted by current surface processes and are now resorting to epigenic cave systems in that.
Mixing.
Yeah, so you see mixing in that. Alexander wrote a very nice monograph on hypogene speleogenesis, and now
This is the Ukrainian scientist?
Yeah, the Ukrainian scientist and that who's we've just heard from him. He's in Kiev right now. Wow. And dealing with all those issues. I one time made a mistake of calling him a Russian, and I got a two-hour lecture on the history of Ukraine. And don't ever do that again.
Yeah.
And that was before the Russians had invaded Crimea. So there's no love lost there. And Alexander is the one who's really been probably the person who really helped me consolidate what I think is my understanding of how the Edwards formed.
Wow.
It explains a lot of the permeability issues. It explains some of the issues with features that we see in caves up in the recharge zone.
Yeah.
And it can be used to help us understand and manage the system. But the biology, just to step back and talk about that. So we have catfish that are found in the deep portion
Leeches
of the Edwards.
And all kinds of stuff.
Snails and shrimp and all kinds. I think the Edwards is the second most diverse karst aquifer in the world, groundwater system in the world, as far as biology.
Yeah.
The one that is that has more, I understand, is the system in Italy is Forsassi caves, and most of that is microbiology.
Wow.
So we have a huge number of species that are found, much of that along the saline water freshwater interface.
Contact, yeah.
So it's very unique. But the question is how did the biology get there?
Right.
And so the biology is trying to tell us something about the processes, the interconnectedness of the conduits. So there's one of 3 or 4 different theories. The first one is that these catfish came in off the recharge zone, washed in, managed to travel across the artesian portion down to the deep saline portion of the aquifer, and over tens of thousands of generations evolved, to these 5-inch long catfish with no eyes and completely white, translucent. Okay.
Wow.
The second theory is that they've come in through the springs, and they have swum, from Comel Springs.
Going against current.
Well, yeah, but the current's probably not, once you get out of the, the area where the discharge is occurring, and so you have a larger area of flow, the current's probably not that hard to swim against, I would think. I may be wrong. But obviously they got in there somehow. And they may have come in through the springs and over tens of thousands of generations adapted to this habitat where there is, the bacteria, what are called autochemotrophs, bacteria that are living at great depth. The water at that depth is warm. It's in the 90s Fahrenheit. So these guys have evolved that. The third thing is that they could very well be silicon-based life forms that are evolved completely independent. Because I saw that on Star Trek, and that may be the other option. I think I'm really going with explanation number 2. They probably came in from the springs, but to be able to follow through the aquifer, there's got to be large enough conduit, interconnected passages or pores that the fish can swim 20 miles, from Comel Springs or San Antonio Springs. Maybe they entered those springs, and they were able to basically, reach the saline water freshwater interface and develop a niche, because we don't see evidently the diversity of biology in the areas that are away from the saline water freshwater interface. So we seem to have biology that's adopted to the epigenic processes in the recharge zone that are going on now. We have some salamanders that are found, let's say, in some of the caves in that area, and some other critters. But most of the biologic diversity is found along the deep, artesian portions of the aquifer, and not in the middle. So we know that they're not living off of detritus because the water wells in the deep artesian portion of the aquifer don't get muddy.
Wow.
So they're living there in this basically along this chemical gradient, and completely independent of photosynthesis.
Yeah.
So we basically, when I went to school, we learned that the sun basically drives all the biology in the process, and
not the case.
And that's not the case here. So these things are probably they're more like some of the bacteria and other biology that's been found in the deep vents.
That's right.
Yeah. So,
wow.
Yeah, these aren't the vents. The vents are hot.
So you can almost argue that you have continental vents. These are almost a continental vent.
Well, the vent is probably not a volcanic vent like you're seeing on the rift zones.
Right. It's more obviously connected to the deep, but maybe
but it's a depth of circulation issue. It's the we know that the depth of the water in the Edwards is warmer because it's 3,000 feet below the surface or 2,000 feet below the surface.
Right.
And
but
probably
maybe there's a connection to a deeper process, like some of these Uvalde and Bastrop serpentinization vents. These igneous vents are all over the Balcones.
Could be. Yeah,
that's a heat source.
Yeah. So so it's complex and it needs a lot more study.
Heck yeah, it does. And where's the funding going? I don't know. It's frustrating, but the funding to solve these things or to study these things in greater detail, that should be a high priority. Better understand this system. We're talking about the freshwater system that's keeping these cities thriving and not in scarcity.
Yeah,
pretty important deal.
Yeah. So we've done dye tracing in the Edwards, which is probably the most difficult place to do dye tracing in the country because of the flow paths.
Wow.
The large number of public water supply wells. So we've done dye tracing up on the recharge zone where we've determined that we've got groundwater velocities of well over 1,000 feet per day to as much as a mile to a mile and a half per day, flowing off the recharge zone south into the artesian zone.
Moving, huh?
We have also done some dye tracing around the springs where we've injected dyes, and we've seen groundwater velocities there of a couple thousand feet per day on the Edwards on the recharge zone over by Comel Springs to slower velocities, around in the deep artesian zone. And I think we were probably the first people to do a dye trace in the artesian zone in the U.S. Where we injected dye down a well 600 feet deep or 800 feet deep, and had it come out 36 hours later in the springs. Got beautiful dye recovery curves and things.
Wow. What's happening to the contact as we drain it? We're kind of getting into the completion part of the PB podcast now, where we're kind of talking about like the studies of the future and these aquifers that we live on, or what's changing. What's your thoughts on water and kind of where it's going? But one of my questions to start that off is, this contact there's a natural process that's driving this geologic contact of the bad water line. There's definitely there must be a pretty major density change between the bottom and the top of that, and it seems like in geologic time it's getting more to the south, more to the north. It's getting larger. The freshwater part of the system seems to be getting bigger. As we pull from that to use the freshwater, how do you think that's making that contact change?
Well, the permeabilities in the saline water seem to be an order of magnitude or more lower than you would see in the freshwater zone. So some of the large well fields that are located right next to that interface during low aquifer periods don't seem to be able to draw that saline water into the wells. So even though they're pumping large volumes of water, the permeability is so great in the freshwater zone that it doesn't seem to be a concern. It was initially discussed as a concern that if we overpump the aquifer, we could end up with saltwater intrusion and causing some of the wells to shut down. But data that we collected during some of the drought periods of water quality, looking at these large pumping wells in the freshwater, doesn't indicate that we've been able to pull it down even during severe droughts.
Wow.
Yeah. The other advantage to these karst aquifers is that they recharge very quickly. So when we have a drought, aquifer levels drop, but if you have a large storm event or a series of storm events, especially in the winter, then the aquifer will recharge. And so the highest water levels in the aquifer actually occurred in the early 90s, and we've approached those a couple of times in the 2000s. So we've seen large drawdowns during droughts. We've seen large recharge events during major storm events. So the amount of water that can be withdrawn from the aquifer also is limited by regulations through the Edwards Aquifer Authority. And so there are no more basically permits that are being issued. So the total amount of water has been capped. And during droughts, people are required to reduce the amount of water that they're pumping. And that will maintain spring flow, discharging from the springs. Because the springs are important ecological resources also. There are a number of endangered species that utilize the springs and basically are found nowhere else in the world except in Comel and San Marcos Springs.
Wow.
So the U.S. Fish and Wildlife and the Edwards Aquifer have worked together to develop a conservation plan to make sure to protect the spring flow to preserve those species.
Yeah.
So
nowhere else in the world. These are types of fish?
Yes. There's the fountain darter. There are a number of different beetles and insects. There are a couple of salamanders there. The Texas blind salamander, which was the very first species listed on the endangered species list when the act was passed, is found in only a few caves in the San Marcos area. So there's been a lot of research and a lot of work done to better understand the life cycles of these animals and to protect them.
Wow. So how about funding? Let's talk about where you see, the rules and regulations that's driving federal funding, state funding, and private funding towards better understanding these systems and these processes and these species.
So water withdrawals from the Edwards Aquifer are regulated by the Edwards Aquifer Authority. And they generate revenue by having people who are users that withdraw water from the aquifer pay a aquifer fee, and the board of the Edwards Aquifer can basically determine what that amount should be.
Okay.
And so so each of the users have a permit, and they will basically pay on either the volume of their permit or the amount of water that they pump. That generates revenue for the Edwards Aquifer Authority, and one of the components of the Edwards Aquifer Authority is a research program.
Nice.
Yeah.
How much money do they take in? Do you know?
I don't know what the budget is for this year, but it's in the millions.
Millions of dollars every year goes into the research.
Well, into the research and to running the Edwards Aquifer Authority, and also the Habitat Conservation Plan maintenance. So there's a fair amount of money through the Habitat. Yeah. Okay. There you go. Yeah, I've got to stretch my back out a little bit.
Yeah.
I would have to dig you up the more recent funding numbers, but they're all online. But the budget for the Edwards Aquifer Authority is, I think, around $15 million.
Wow.
And
a year.
And that money will go to administrative costs,
sure,
research, Habitat Conservation Plan funding, et cetera.
Man, so that one entity is researching fresh water versus maybe the saline water, kind of how that contact's moving, what's happening in the aquifer, the species of the aquifer, and in the springs.
Right.
It's doing
So there's an extensive monitoring program to look at water quality across the aquifer to see if there's degradation that may be occurring.
Yeah.
So a number of wells are sampled, and it's one of the things that we implemented when I started working at the Edwards Aquifer Authority 22 years ago, and I retired last May.
Wow.
Yeah. So was to initiate a water quality sampling program that runs from basically Uvalde to the springs. And many of the wells are sampled either yearly or quarterly, again, depending on the location and interest, for a very wide range of parameters. When I got here, there were wells across the saline water freshwater interface that were being sampled for metals and what I call wet chemistry, cations and anions.
Nice.
We've expanded that to include herbicides, pesticides, PCBs.
Nice. What about metals? You're looking at all the different
all the metals.
Is that right?
Yeah, and volatile organic compounds.
Is that
and
right?
Semi-volatiles. And
Hydrocarbons?
Basically, they would appear either as VOCs or SVOCs.
What
Volatile
about
organic
DOC? The dissolved organic.
We do some of that, but again, that's modified.
What's
and
VOC?
A volatile organic compound. So that would be benzene to, on up from benzene and toluene and ethylbenzene and xylene and all the other
Is that heavier
VOCs.
aromatic stuff or what?
Yes, and then the semi-volatiles are your heavier compounds. And that, so US EPA has got a suite of analysis that you commonly do
That's
for
interesting.
For
how about
volatile
lithium?
organic compounds.
Any anomalies in lithium?
I'd have to look at the data, and I'm not sure that lithium was one of the compounds we've looked at.
Oh.
Yeah, strontium. There are some interesting things with strontium that can maybe be used to help define contributions from the Glen Rose aquifer up on the contributing zone. Seems to maybe have a little bit different signature. But the part of the problem of trying to determine your water balance is to determine where water is coming from and going to, is looking for unique components in the water. And the problem with the Glen Rose is it's also a limestone.
Yeah.
And so it's really hard to differentiate those.
Right.
But there's some good folks working on that at the Edwards now, and some folks with.
Is all that publicly available?
Yes.
I can pull all that data?
You could pull. You certainly pull the historic data. Whether this year's data is available for you or not is a good question. But, previous years they publish it and it's on the web.
Elemental data, all that stuff's out there.
Yeah.
Man, that's
Yeah, it's
fantastic.
pretty-
I'll have to shoot some emails back and forth with you to show me some links that I can dig into some of that.
There's the hydrologic data reports are out there, and it includes everything from rainfall, water levels to chemistry.
Right
And
on.
that's been published every year.
GIS mapper that kind of has it all in place, or you got to kind of still put that together?
You may have to put that together. Again, I don't know if that material's on the webpage or not.
Certainly there would be some XY coordinates of where,
absolutely.
where that's coming from. Mm-hmm. That's cool.
Yep.
So easily mappable if it's not already.
Right. And, it's all on the webpage there, but you may be able to also ask for an ASCII file and download the data.
Cool. Nice. You can contact one of the guys. And,
right.
Oh, that'd be great.
Right. Yeah.
That would be super great. Now, what $15 million does sound like a lot of money, but are they doing any kind of public forums and public events where they're looking for private funding to help beef up this effort to map these changes and better understand what's going on in the ecosystem?
Yeah, well, the Habitat Conservation Plan has a number of different funding sources.
Okay.
And so they're obtaining money, I believe, from Fish and Wildlife, certainly from the Edwards Aquifer, but from all the other folks who have signed on to the Habitat Conservation Plan. So there is a mechanism there for obtaining either in-kind services or funding. But those areas, I'm not as familiar with because it's been a couple of years since I've really worked with those numbers. So to look at the contributions from individuals and that. I know that there's also the Edwards Aquifer Foundation, which is being used to raise private money. And there have been efforts to try and obtain grant money for research.
Nice.
And also to support scientists and others who are working on work.
Right.
Yeah.
So, there's the Garys of the world that are out there that have this, natural affinity to study this stuff, and they really enjoy, that and mapping caves and not just mapping the size and shape of them and like what sediments and what the water's doing, but the elemental makeup of the walls. We have handheld tools now that you can get down there and you can start mapping the elemental change of the aquifer and its heterogeneity from one side to the other. It's really interesting. I have some data and some ideas from MagmaChem and doing research with them that these metal anomalies in aquifers could be representative of the aquifer itself. There could be metal anomalies in the carbonates or in the sands. You just got to do that work. You got to compare. You got to core it. You got to get the cuttings, and you got to do the work on that to know that. But maybe some of those anomalies are driving some of the anomalous medical conditions in the community. So there's a tie there that some of the aquifer could be contributing these metals that are potentially contributing to these health issues and the anomalies there.
Now I know that we look at the water quality data and compare it to the Safe Drinking Water Act criteria. And there are very few parameters that exceed the maximum contaminant limit for parameters in that. The water quality in the Edwards is actually quite high, very good. But there are places where it has been degraded due to human impacts in that.
Wow.
Yeah. There's a number of cases where there have been detections of gasoline. In some of the recharge wells, there's been other issues with some of the solvents that are associated with possible landfills up on the recharge zone, et cetera. Mm-hmm. So there's some issues, and I think the EAA does a good job in trying to track those and keep an eye on them. And that there have been a few wells that have had to be closed that had exceeded contamination levels.
Yeah.
So. But by and large, the water quality actually is surprisingly quite good right now. However, considering we're building up onto the recharge zone, and with the urbanization, basically in suburban sprawl, one of the concerns is degradation, both from non-point source contamination, but also through things like sewer releases. So we've had a number of sanitary sewer breaks up on the recharge zone. And one of the concerns is that they would impact. So, you talk about water quality issues with metals or herbicides or pesticides or VOCs. What I lose sleep about, or used to lose sleep about when I worked on there was pathogens and potential, breaks from sewer lines. So, if you dump 500,000 gallons of raw sewage onto the recharge zone, Yeah, where's it going to go? How quickly is it going to get there? What wells are it going to impact?
Right.
And people, if you think about it, the concentrations, the contaminant levels that are allowed by EPA are generally based on toxicological studies associated with increased risks of certain cancers and or other acute health effects or chronic health effects over drinking the water for very long periods of time. So let's say, for example, the concentration allowed for benzene is 5 parts per billion, which I think, if I remember right, is 5 seconds in 32 years. These are incredibly small numbers. And so to increase the risk of generating a certain percentage of cancers over a lifetime, they set that limit very, very low. Pathogens, on the other hand, are something that can make you sick if you ingest the water tomorrow, and can result in a number of ill health effects.
Wow.
And there are some well-documented case studies in karst aquifers where people have been exposed to pathogens and resulted in all kinds of issues.
Wow.
The Walkerton, Ontario, Canada case in the early 2000s, or late 99, early 2000s, where I think 5,000 people, a city of 5,000 people, 2,500 of them got sick. And I believe they had 7 or 8 people die.
Oh, shit.
And a number of people who had serious damage to kidneys, stomachs, and livers from drinking, water that was contaminated with fecal coliform.
Oh my gosh! So there was a break in the sewage line somewhere in the discharge. That whole system.
It was actually related to application. And my understanding is it was related to application of animal waste on a karst landscape that then flushed into a sinkhole that then went into a well, and the chlorinators were not working, and so people were getting sick. Some of the early cases, the people thought it was food poisoning, so the doctor said, well, make sure you stay hydrated, drink plenty of water.
Oh, my gosh.
And there was actually criminal cases, there were a number of people who mismanaged the water system, and those people went to jail.
Oh, my gosh. Very serious.
Yeah, so if you get a chance, read the case histories of that.
I will. Geary Schindel, thank you so much for sitting down and taking time to tell your story and teach us about what's going on out here.
It was a nice ramble. And thank you for inviting me, Troy. I really appreciate it.